So the photon clock is a real thing. It is a real piece of equipment that physicists can use to conduct the experiment that I'm going to talk about. And basically understanding the photon clock will essentially make you understand the theory of relativity. It's the most important thing in this video. You can trust my words on that. And I think this is perhaps one of my biggest takeaways from this course, Origins and Meanings. And basically, the design is simple. You have a bottom plate, you have a top plate, it's a device, and you fire a photon, which is a light particle. So light particles travel at light speed from the bottom plate to the top plate. And because the plates have a set distance, that particle is going to take a fixed amount of time to get to the top. I mean, think about it. Distance over the constant velocity of light, right? Constant distance over constant velocity equals to a fixed time. So tick tock goes up, bounces down. Let's just call that 1 unit of time. So tick tock, 1 unit of time, tick tock, 2 units of time. Everything seems fine. And at this point, nothing strange is happening, but you should keep in mind this notion that 3 times 10 to the 8th power, that's a huge number. That's the speed of light. I mean, that is immense. But at the same time of being just this astronomical figure, you have to think about it as sort of a cap too. Because it's fixed, it cannot go slower than that, but it also cannot go faster than that. And this is where things get really weird, because what we're about to do essentially is we're going to ask light to go faster than that. But it just cannot do it. Okay, let's say we have this photon clock that was so nicely set up before, just bouncing up and down, tick tock. And you start moving this photon clock towards a certain direction. So if you can imagine in your head, tick tock. If you're moving towards the right, for example, it actually makes a zigzag motion, right? I mean, it's bouncing, but you've added a horizontal thing to it. So it's like doing a little zigzag motion, if you can imagine that. And everything seems still fine at that point until you look really closely into it. Because, okay, so in the stationary example, light is going up at full speed. I mean, it's only got one speed, and that's the full speed, 3 times 10 to the 8th power. But right now, this device has got a velocity to the right side, right? I mean, it's moving to the right side. We're pushing it to the right side, and the photon inside has to go with it to the right side. So light was already traveling at its peak speed, going up and down. But now we're asking it to also add in this horizontal velocity to the right. How could light do that if light speed was constant? How could it go up and down at the same speed as before, and in addition to that, also travel to the right? The fact is, light cannot do that. This 3 times 10 to the 8th power is huge, but it becomes a cap. It becomes a cap so that light cannot move 3 times 10 to the 8th power this way and have that little horizontal thing. So right now, all it can do is move 3 times 10 to the 8th power in a very diagonal way, along that zigzag line. If you think this through, if you're devoting 3 times 10 to the 8th power into that diagonal line, that means your up and down speed actually decreases from 3 times 10 to the 8th power. So originally, you were having every single piece of mind that light has, you were just going up and down. But right now, light's being distracted. It's being distracted by this horizontal motion. So now it has to distribute some of its original up and down speed to go to the right, because you cannot exceed the cap. If you exceed the cap, then sure, you can maintain both up and down same speed, and you can move to the right in addition to that. But right now, light cannot. So you're moving along the zigzag line, and basically light distributes part of its velocity that was originally distributed to moving up and down, but now distributed to moving sideways. So the up and down has to decrease. And the 3 times 10 to the 8th power becomes a cap. So let's think about this. You have this photon clock on the left side, and you have this moving photon clock on the right side. The stationary photon clock, tick-tock, tick-tock. Sure, let's just call that standard time. Let's just say I'm on that clock, and I'm stationary. I'm experiencing this tick-tock, tick-tock, 1 unit, 2 unit, 3 unit. And now you've got this moving thing. This moving thing, however, as I mentioned before, the photon doing the zigzag thing, the up and down speed has to be distributed to the horizontal speed. So up and down speed slows down, so it tick-tocks slower. So essentially what it is time slows down. Let's go through this again. Because light has a cap at 3 times 10 to the 8, because it's constant, it distributes part of its vertical to the horizontal. So the vertical slows down and time slows down, because we were saying that tick-tock, tick-tock was what measures time. And one important thing that I think is key to this is I've always had this question. Who gives you the right to say that this tick-tock is time? You know, what gives you the right to say that? Maybe something else is time. Why do you say the tick-tock is time? And my answer to my own question is that if you were on that moving clock, this is the most exquisite part about this experiment. If you were on this moving photon clock, you would still see light using all of its energy moving up and down, all of its pieces of mind traveling up and down. You would not see light being distracted by the horizontal motion, because you're moving along with light if you're on that photon clock, right? So the horizontal part of the thing, of light, you cannot see. And all you see is the vertical. So to you, light is traveling at same speed, 3 times 10 to the 8th power, going up and down. So to you, time isn't slowing down. To the stationary observer, time does slow down, because the stationary observer is able to observe the horizontal component of the moving photon clock. But whoever's on that photon clock cannot observe that horizontal component. All they see is the vertical up, down, and the constancy of the speed of light at 3 times 10 to the 8th power going up, down, up, down. Time seems fine to them. And you see this discrepancy in time, that both parties can claim that the other party's time was slowing down. And that is just an incredible phenomenon. So one thing led to another, and we started from velocity and speed needing to be relative to something to now the singularity that light's velocity is not relative to anything else implies that time can slow down. And I really take interest with the idea that time slows down, because it opens up so many interesting possibilities. I first like to address how much does time slow down. So if we go back to our photon clock example, I really like photon clocks, apparently. And in a photon clock, it has a horizontal velocity, and light has to sort of carve out some of its vertical to devote it to the horizontal. But what if the horizontal was so large that it takes up almost the entirety of light's speed? What if you're going at 99.99% horizontally? That means light is so exhausted following the clock that the up and down motion becomes so insanely slow. What this means is a drastic slowing down in time for the person on the clock. So from the perspective of the stationary person, as he sees the clock traveling that way, that person is moving in extreme slow motion. So basically, the faster the horizontal speed for the moving photon clock, the more drastic the slowing down of time is. And on a personal level, this actually is so incredibly world toppling because it opens up a lot of possibilities. I mean, right now we don't have the technology to make human beings go near light speed, but I do believe in the near future when we do, there are so many interesting conversations to be had. I mean, one possibility that I thought about to myself is what if, let's say someone has pancreatic cancer and right now we just don't have the technology to save him. What if we put him on that ship? Of course, there's a photon clock on the ship too. I mean, it doesn't need to be there, but it's better if there is one for experimental purposes. Let's just say there's a photon clock on that ship. Light traveling with the sick person with the ship near the speed of light. The photon clock positioned horizontally needs to devote so much energy following that ship that the up and down becomes so slow. So 1 second of that ship can mean maybe 100 years. 100 years is a little bit extreme. Not even sure if humanity still exists by that time, but let's just say 10 years. Let's just say a second is 10 years. So by the time they fly back, which is like 5 seconds later, 50 years have passed. And maybe by that time we have the technology to save the sick person on the ship, even though it was only 5 seconds for him. So he's definitely still alive. And think about that. What if he only had 2 months to live? This basically just prolonged someone's life. I mean, the implications of this are endless, and all of them are affecting people. At least me, in very visceral ways. So to end today's video, I want to talk about some very personal implications that the theory of relativity had on me. Not physically, but I always keep this idea in my mind wherever I go. I should probably see a doctor for this, but basically any movement at all invokes the theory of relativity. Time slows down, no matter how small the movement is, because when you think about it, if we go back to that photon clock, the light was going up and down at full speed already. And no matter how much you ask it to move horizontally, it is going to take away some of that vertical speed. But remember that vertical speed is 3 times 10 to the 8th power. I mean, that is nothing close to what we encounter in everyday lives. So pretty much it's negligible, but for some reason I just cannot get this out of my head. Okay, thank you guys so much for watching today's video, and I hope you guys enjoyed it. I'll see you next time.